right, quick recap. This is Kepler's third law, p squared equals a cubed. This is the more general form that came from Newton's law of gravitation, that the period squared is 4 pi squared over gm a cubed. Okay? So for our class, we're mostly going to be using this one, because we usually don't use units of years and AUs, and this only works if you're going around the sun. This works for any object going around any other object. You just have to put in the mass, and this is technically the total mass of the objects that are orbiting each other. All right, so make sure you know Kepler's laws of planetary motion. We're going to talk about that now, because we're going to talk about satellites and things in orbit. This works for anything orbiting any other object. Okay? Now, let's talk about like putting a satellite in orbit around the Earth. Newton was the first one to realize that you could actually orbit an object around the Earth. He had a drawing of a cannon on a mountain. And he said, look, if you shoot a cannonball out of the cannon, what's going to happen? Here's the center of the Earth. If you shoot it out, it's going to go and it's going to fall to the Earth. But what it's really wanting to do is to actually make an elliptical orbit around the center of the Earth. Center of mass of the Earth. That's what it's trying to do. And when it does that, all we see is this part of it right here, because then it hits the Earth. But it really is making an elliptical orbit around the center of the mass of the Earth, where the cannon is at the furthest point in the orbit. Or we would call this an apogee. This is perigee down here. Remember, we have perihelion and aphelion? Well, if you're going around the Earth, you turn it to G instead of helion, because helios means sun in Greek. All right, but Newton said, okay, well, what if I fire the cannon harder? I put more gunpowder in so it goes farther. Well, then it's going to go out like this, hit the Earth, but it's still trying to make an elliptical orbit back to the cannon. And if I fire it fast enough, if I get the speed going fast enough, it's going to start falling, but it's going to fall around and miss the Earth and come back to where it started. So he realized to put something in orbit around another object, all you had to do was get it going fast enough. That's what all our rockets do. If you want to put something in orbit, you get it going fast enough. Let's calculate how fast that needs to be. If you're out here, so I put my cannon and it's orbiting the Earth, what forces are acting on it? Now when you think about it, this is really easy. There's only one force acting on it. It's gravity. So here's my object, my satellite. Let's put this as a satellite here. My satellite orbiting the Earth has one force on it. It's gravity. But look, we can't put mg in here anymore, because remember, our little g only works if we're on the surface of the Earth. So we have to put in Newton's gravitational formulation. This is m1, m2 over r squared, right? So we're going to put that in for the force of gravity. So we're just going to do F net y, or x in this case. And it's going to the left, so I'm going to put, minus g, m1. We're actually going to do mass of the Earth, mass of the satellite, over the radius of the Earth plus the height squared. So this is the radius of the Earth here. This is the height it is above the surface of the Earth. Okay? Or, to make this simpler, I'm not going to call it that. We're just going to call it r, the radius of the orbit. So we're going to just call this distance r, but it's the sum of that. It's actually how far it is from the center of the Earth. We're just going to call it r squared. But remember, it is the sum radius of the Earth plus the height above it. But what kind of motion is this? This is circular motion. So we go all the way back to chapter 4. When you said we dealt with circular motion, it says, what do I have to replace F net x with? Well, there has to be a centripetal force to keep it in orbit. And it's going to the left, so this becomes minus mv squared over r. This is the mass of the satellite. So you go minus g me ms over r squared. So the negatives cancel. I can also divide out the mass of the satellite. And look, I can get rid of one of the r's. So this simplifies massively. And I get that v squared is equal to g me over r. Or v is the square root of g me over r. That is the velocity you need to be going to put something in circular orbit around the Earth. Most of the time for the Earth, at a distance here of about 100 miles up or so, this is around 17,000 miles an hour. So when you're riding in your space rocket, you want to get to the International Space Station, you go from 0 on the ground to about 17,000 miles an hour in about 5 to 10 minutes. That's how much the rocket has to accelerate you. And so you pull a lot of G's. That's why astronauts have to be in very good shape, because it's really intense for those times. They pull 2 to 4 G's for that long time. Most people can handle a couple of G's easily. I mean, that's what you get on roller coasters and stuff, but you get it for a very short time, for a few seconds. They have to pull it for several minutes until they get into orbit. So that is the orbital velocity of anything in a circular orbit. You would just change, if you're going around the moon, you just change the mass of the moon and the distance you are away. That's a constant, remember, it doesn't change no matter what. All right, so let's now talk about energy. Does this have energy? Yes. And the great thing about objects in orbit is their energy is conserved through the whole orbit. And so if we can get their energy, their total energy, their potential plus their kinetic, that'll be the same no matter where they are in their orbit. And so you can use that to figure out how to change from like one orbit to another. Now, the way we do this is a little different before. Remember when we did potential energy? We used to call it mgh. But that works if you're on the surface of the Earth, and h isn't very big compared to the radius of the Earth. But when you start talking about things in orbits, you can't use little g anymore. And h becomes very, very large, so it's changing your r, so that doesn't work. So you can't use this for objects in orbit. Okay, it doesn't work for objects in orbit. Or objects even going around some other object. So we have to use a different formulation. So we use that the potential energy is equal to Gmm over R. Now, the other thing that we do with the potential energy is we set the 0 point to R being at an infinite distance. You're like, what? This doesn't make sense, and it is. It actually makes total sense. The more you do it, and rocket scientists realized this a long time ago. Because remember when we were using this, we always said, oh, you can set 0 wherever you want. And then you measure from that point. And it will work if you pick it up here or down here. As long as you measure from that point, you can have negative or positive potential. Well, in space, there's no real good reference point. And so the easiest thing to say is let's set 0 gravitational force at an infinite distance r, right? If r goes to infinity here, this is going to go to 0. Remember, if you make the bottom very, very large, these are going to stay the same. That's going to go to 0. Now, the only challenge is that makes this potential energy negative. Because if 0 is out there an infinite distance and you get less than that, less than infinity, it's always going to be negative. So gravitational potential here, that should be U, is always going to be a negative value. Right? But that's okay. It works, and it works really well. It makes life easier to figure things out. Kinetic energy hasn't changed. kinetic energy is just 1/2 mv squared. So let's say we want to figure out how fast do you have to go to escape Earth's gravity. This is not hard to do. We're going to say, okay, here we are. We got our rocket sitting on the surface of the Earth. We need to know how fast we go so that we're not stuck in the Earth's orbit or anywhere close to Earth. We get away from Earth's gravitational pull. Remember, we have to get up to this velocity to get in a circular orbit, but we still haven't escaped Earth's gravitational pull. We're still stuck in this circular orbit. To escape completely, you have to go faster than this to get away from the pull of gravity altogether. We're going to do that with energy. All right, so we're going to say energy initial is equal to energy final. All right, so we're going to start out here at the radius of the Earth. So we have gravitational potential here. We have no kinetic because you're going to start out the rocket and just sitting on the pad. It's not moving. So this is going to be minus g, mass of the Earth, times the mass of the rocket, divided by the radius of the Earth. That's your gravitational potential. On this side, we're going to have gravitational potential plus kinetic energy. So the gravitational potential, but we're going to do it at an infinite distance, because we want to escape the Earth. So this becomes